All right. So today we're going to talk about potential energy and mechanical energy. Woo! Okay. So I'm going to describe when something has or does not have gravitational potential energy, how much mechanical energy something has, when it's conserved, how to calculate stuff, and we'll get to the energy bar charts later. Okay, gravitational potential energy. Um, this is the energy, the stored energy something has when gravity has the potential to do work on it. The stored energy something has when gravity has the potential to do work on it. You guys can read that, right? Uh, hmm. That's why your reading quizzes stink. Good job. All right. So the equation for that is mgh. You might remember that from middle school. Maybe. Okay. I don't know. Middle school is a blur. And it's energy, so it's a joule. Every type of energy is in joules. Okay. This you don't need to know. I'm just for those who are like curious. So let's say you have a rock on a cliff, okay? Has a certain mass, certain height, okay? Um, gravity has the potential to do work at this location, okay? If it falls, you have a force of gravity. The work is equal to force times distance. The force, don't worry about writing this down. This is just for those who are curious. This is force times distance. The distance would be the height. Well, force of gravity equals mass times acceleration of gravity. So the work, as if this falls all the way, would be equal to the force of gravity times the distance, mgh. So this has, in this location, this has the potential, gravity has potential to do that much work on it. Good with that? Okay. Potential energy. All right. Mechanical energy. This is the sum of kinetic energy plus potential energy. The sum of kinetic energy plus potential energy. Okay. Don't worry about the T. It's just they use that for total mechanical energy, but mechanical energy. Okay. So this is the energy that we care about in physics. Kind of a lame definition, but okay. Good with that. All right. Every type of energy is in joules. Work's also in joules. Okay. Mechanical energy. When is it conserved? This is a really big concept in this class. Okay. So, when something is conserved, what does that mean? Conserved. Not used, saved, doesn't change, stays the amount stays the same. Okay, so we're gonna say stays the same. The amount does not change. Okay, so the mechanical energy of an object is conserved if there are no non-conservative forces there are no non-conservative forces. Okay, you can see that. You guys see that in the shadow? Okay, no non-conservative forces doing work on the object. There are no non-conservative forces doing work on the object. Now, I recognize that this definition begs a lot of questions. Like, what's a non-conservative force? What's a conservative force? What are we talking about? Just write it down and I'll let you know. Okay. So, conservative force. Conservative forces. Gravity is a conservative force. Spring force is a conservative force. Electric force of attraction or repulsion, conservative force. Magnetic force of attraction or repulsion, a conservative force. Okay? These last three, don't worry about them. We are only going to use gravity. Okay? We'll talk about electric and magnetic next semester. Spring force, we don't have time for it. We're cutting our losses. Okay? So, the only force that you care about in this list is force of gravity. Good with that? So if you're like just looking to get the grade, gravity. Okay? So if it's not a conservative force, then it would constitute as a non-conservative force. Non-conservative forces is everything else. Okay, if it's not a force of gravity, it is a non-conservative force. So I won't ask you about this, but this is for the people who are curious, like, well, why is gravity conservative? Why is everything else not conservative? Conservative force is deemed conservative if that force is only determined by, or excuse me, the potential energy is only determined by location. Okay? It has a certain amount of potential energy at this location, at this height. I can move this around, go all over the place, jump up, and I come back to the same height, and it has the same amount of potential energy, gravitational potential energy, because of the location it's at. Okay, that's kind of a rough explanation of what makes something conservative versus non-conservative. Okay. So, you remember in elementary school, maybe middle school, learning about the law of conservation of energy. Energy cannot be created or destroyed. Okay. This law of conservation of energy is a big picture energy. Mechanical energy is a subset of energy. Okay? We can gain and lose mechanical energy. That does not disobey the law of conservation of energy. Okay? Because it can be converted into like heat or light or sound or whatever other type of energy. Okay? Get to that. Okay. We're not worried about that. Okay. Around G to 10. Okay. So, correct answer is D, dangerous dinosaurs. Okay. If this book just stays on this table and doesn't go anywhere, the lowest point I care about is the tabletop. So I'm going to say ground zero is going to be the tabletop. And it has no potential energy. Okay. If this book in the story problem falls off the table and lands on the floor, the lowest point I care about is the floor. So I'm going to make this the floor, ground zero, and therefore it's going to have a height of 1 meter and it'll have 20 joules of potential energy. If, in some weird scenario, we have an earthquake and the floor breaks open and the book falls from the tabletop all the way to the ground, then the lowest point we care about is the earth below, dirt, and it's going to have 120 joules potential energy. Okay, so potential energy is relative. It depends on where you define ground zero. Okay, and where you're going to put ground zero is the lowest point you care about in the story problem. Okay, so there's a choice there. You have to declare, hey, I'm going to make height 0 at this point. Okay. All right. Give this one a shot. Okay, thumbs up when you have a guess. You will see next semester. Okay. To determine this, what we're going to do is we're going to look at the forces acting on it. Okay. Free body diagram. Good with that? Gravity, is that a conservative or non-conservative force? Conservative, so we're good. That checks out. Okay. What about normal force? Is that a conservative or non-conservative force? Non-conservative force. Uh-oh. But the condition for mechanical energy to be conserved is not if a non-conservative force is acting on it, is if a non-conservative force is doing work. Is normal force doing work on the object? Talk to your neighbor and tell them why or why not.
My mind.
Okay, is normal force doing work? No. Is there any component of force that's going parallel to the direction of motion? No, it's acting perpendicular to the direction of motion. It is doing no work. Is mechanical energy conserved in this scenario? Yes, there's no non-conservative forces doing work. Good with that? There is a non-conservative force acting on it, but it's not doing work. Thumbs up when you have a guess. Have a conversation.
Yes, that's the answer. I'm pretty sure it does. Sure. You said this.
In order for like mechanical energy to not be conserved, you have to
Okay, what do you say? Is gravity a conservative or non-conservative force? Conservative. Is normal force conservative or non-conservative force? Non-conservative. Is it doing work? No, it is not doing work. Applied force. Is it a conservative or non-conservative force? Non-conservative. Is it doing work? Oh, yes, it is. Is there a component of force that is parallel to the direction of motion? Yes. Okay. Is mechanical energy conserved? It is not conserved. Is the sum of the forces equal to 0 in this scenario? Is the sum of the forces equal to 0 in this scenario? Is inertia doing what it wants to do? Is the car's inertia doing what it wants to do in this situation? Yes. Is the sum of the forces equal to 0? Yes. It is moving at a constant velocity. In order to do that, the total force has to be equal to 0. Okay? I have trained you, maybe or not. I've tried to train you to identify when the sum of the forces are equal to 0 or not. If it's moving at a constant velocity, the sum of the forces are equal to 0. This is a different condition for if mechanical energy is conserved or not. Okay? In terms of energy, since you're moving at a constant velocity, your speed is not changing. Therefore, your kinetic energy is not changing. You right with that? But mechanical energy is not conserved. Okay? To go a little bit deeper, is applied force doing positive or negative work? Doing negative work. Is everybody good with that? It's being forced in the opposite direction of motion. Okay? So we have concocted this idea of work to help us understand how force affects energy. If applied force is doing negative work, that means it's taking away mechanical energy. We're decreasing mechanical energy. All right with that? Okay. Okay. Follow me on this one. Thumbs up, thumbs down. Yes, no. Okay. If mechanical energy is conserved, does that mean mechanical energy is staying the same? If mechanical energy is conserved, does the amount of energy, mechanical energy, stay the same? We say mechanical energy is conserved, is the amount of mechanical energy staying the same? Thumbs up, thumbs down. Yes, that is true. If mechanical energy is conserved, is the amount of mechanical energy changing? If mechanical energy is conserved, is the amount of mechanical energy changing? Thumbs up, thumbs down. If it is conserved, it is staying the same. Therefore, there is no change in mechanical energy. Good with that? If mechanical energy is not conserved, is mechanical energy changing? If mechanical energy is not conserved, is mechanical energy changing? Thumbs up, thumbs down for that question. If mechanical energy is not conserved, is mechanical energy changing? Yes, it will change. Everybody tracking so far? So, change in anything is final minus initial. Okay? I have found that people don't do well when equations have negative signs in them. It's just a source of error. So, what I try to do is, if I can, alleviate negative signs, subtraction. So I'm going to bring this over here. So I have initial mechanical energy plus the change in mechanical energy is equal to the final mechanical energy. All right, with that, let's make comparing energy to money is a really good analogy. Okay, let's say we have initially $100 in the bank, and I deposit $20. That's my change. What's my final amount of money in the bank? 120. Let's say I start with $100 and I take out $30. I withdraw $30. I've got 70 in the bank. Everybody tracking? Good with that? Okay. Now, I'm going to come back to work, this idea of work. Okay. We have concocted this measurement of work to help us understand how force affects energy. Okay. When a force, a non-conservative force, acts on an object over a certain amount of distance, it does work. Okay, this NC represents non-conservative. Okay, it does a certain amount of work. That work done is actually equal to how much mechanical energy changes by. Because we know that if a non-conservative force does work, mechanical energy is not conserved. It changes. But by how much? You know what? It's equivalent. It's equal to how much work is done by that non-conservative force. That's why we have this idea of work. See how force affects energy. Good with that? So what I can do is I can use this. So let me go a step further. If a force is doing negative work, like we saw in this problem, doing negative work, therefore it's causing a negative change in mechanical energy. I'm taking energy away, mechanical energy away from the car by doing negative work. Okay? If I was doing positive work, I have a positive change in mechanical energy. I'm giving energy to the car. You all right with that? Okay? So I can take this expression and I can substitute it in for here. The green and the black are synonymous equations, the same exact equation. Okay. Sometimes in a story problem, I'll say, hey, you're going to lose this much energy. Sometimes in a story problem, I'll say, hey, you're going to do this much work. These two statements are the same thing. Good with that? Okay. Getting close. Okay. So mechanical energy is equal to the sum of kinetic plus potential, right? So I can take this expression and I can plop it in there, substitute it in here and in here. So this gives me this equation I'm going to write in blue. You are going to be well familiar with. This next equation I'm going to write, this is going to be your original equation that you're going to be using a lot. So initial kinetic energy plus initial potential energy plus the work done by a non-conservative force is going to be equal to kinetic energy, your final kinetic energy plus your final potential energy. Alrighty? And I'll incorporate the math on this on Monday, but conceptually I want this to like sink in here momentarily. Are we good? All right, this next slide is an archaic animation, but it's very information rich, so I continue to use it. Okay, so we're going down, a skier's going down a frictionless hill and then hits the lower bottom, and there's rougher surface and it experiences friction. Okay, so while it's up here, the free body diagram of the skier, you have force of gravity and normal force. Okay, is mechanical energy conserved as it goes down the hill? Tell your neighbor. Is mechanical energy conserved as it goes down the hill? Hopefully you said yes. Mechanical energy is conserved. Gravity is a conservative force. It is doing work, but that's okay. It's conservative. Normal force is a non-conservative force, but there's no component of that that's acting parallel to the direction of motion. It's acting perpendicular. No work is done. Mechanical energy is conserved. So here's the consequence of that. As it goes down the hill, the total mechanical energy, they like to use T, I don't really care about that. Your mechanical energy stays the same. It's conserved. Here's my analogy. Kinetic energy, I liken that to a checking account, okay, in your bank. Potential energy is like your savings account. Okay, and your mechanical energy, this is how much money you have in the bank overall. Okay, now let's say at the top of the hill you started at rest, so you had 0, you weren't moving, 1/2 mass times speed squared for kinetic, no money in your checking, but you're like elevated. So let's say you had 100 joules, $100 in your savings, 100 joules of potential energy. In your bank, you would have 100 joules total. Good with that? Now, as you go down the hill, we discern that there's no non-conservative forces doing work. The total mechanical energy stays the same. So you can do internal transfers, but that's not going to change how much money you have in the bank. As it goes down the hill, we're decreasing your height. So you're decreasing potential energy, but you're also speeding up. So you're going to increase your kinetic energy. Does that make sense? So let's say you had 20 joules of kinetic energy. How much potential energy do you have now? You have 80, because you know the total money in the bank is still 100. Good with that? Okay. So as it goes down the hill, not helpful. As it goes down the hill, it's decreasing potential, increasing kinetic, but at every point in time, the mechanical energy remains conserved until we hit the bottom, and then we have gravity, normal force, and friction. friction a conservative or non-conservative force? Non-conservative force. Is it doing positive or negative work? Negative work. Okay. So let's say here we pulled out. Let's say we pulled out $40. We withdrawed $40. We withdrew is negative 40. We've lost 40, so we have 60 in here. Does that make sense?
Yes.
Okay. Have a good weekend.
I've made it to 100 grams.
Are you testing it?